All right. You say the prayers.
In Jesus' name.
All right.
Father, we thank you for the moment that you've given unto us to learn. Pray that it shall be a fruitful one. Open up our hearts of understanding in Jesus' name.
Amen. Actually, when I downloaded some free PDF on experimental design, I went through them. I think this one was more simple, explanatory, and not tailored towards agriculture or those kind of experiments. This one was more conventional, like had several cases, examples that apply to real life problems. The other ones were peculiar. Even most of the examples had to do with things we barely have knowledge about. We're talking about hospital situations, clinical experiments, agricultural kind of experiments, things we may likely not understand the terminologies. But when I went through this other one, it was more, it was simpler. Most of the examples were something that we could relate with or relate to. So it's written by Seltman. I think this July 11, 2018 should be the
4 years.
version. Experimental design and analysis. So let's look at what he has to tell us. Try to get it to fit this screen. All right, we are going to skip all this and go straight to chapter 1. Let's see that this is chapter 1. All right, I love the caption that this man gave. It says the big picture, why experimental design matters. Talks about much of the progress in sciences comes from performance experiments. So do we need to read through or should I try? Because I explained this, some of these issues yesterday.
I think the explanation will be better than trying to read through, so we could save time.
All right, this is a cycle of experimental design by this author. So this is your current state of knowledge. You construct a testable hypothesis given a particular question. Like yesterday, we posed some question. And because of the question, we were likely to conduct a research to answer the question. Now, while conducting the research, you must have an hypothesis. You design how you want the experiment to work, and you have an analysis, and then you interpret the report. So this is a circular flow of scientific learning. Please ignore the background noise. So we explained yesterday the importance of careful experimental design, though we didn't use same example. So our goal is always to actively design an experiment that has the best chance to produce meaningful, defensible evidence, rather than hoping that good statistical analysis may be able to correct for defects after the fact. Yesterday, we said that a result of an experiment should be able to represent the population that was experimented upon. That is, every typical data of that population should have at least an attribute, a particular observed attribute of the results of an experiment. For example, when you have an experiment, there are several results. A typical member of the population should be able to have one item in the results. So the results should represent the population that was experimented upon. Here he tried to make an overview of the statistical analysis. We are still going to skip this and move straight to the various statistical analysis and why they are needed. All right, we start here. So you have a question, a scientific question. And Mr. Isaac, can you give any question you think you have in mind?
Maybe determine which year is the leap year between 2000, the year 2000 and 2030.
Okay. So, okay, you say a leap year, particular year is a leap year. All right, what will
Determine
be
between 2000, the year 2000 and 2030,
okay,
the leap years in them.
okay, to know the number of leap years. Now,
Yeah.
what do you think would be the null hypothesis? Because you have already picked the data you want. You have given a range of data. So what will be your null hypothesis? Is that an experiment or a well-defined data that you can sort the answer?
I think it's a well-defined experiment that data can be sorted from.
The data is already there, so you just need to sort it out.
Yeah.
Now, the idea of experimental design is not to sort data. No.
Okay.
The idea of experimental is to model a typical result that
Okay.
meant a population. Example, you might say, everybody in Akwa Ibom State are hardworking. So somebody might ask, now, after making the statement, somebody will say that is not a statement of fact. It cannot represent the population of Akwa Ibom. So you are now meant to conduct a research. So
Okay.
the question now um, is a typical Akwa Ibomite hardworking? So the null hypothesis would be that a typical Akwa Ibomite is hardworking. That is, Mr. A is as hardworking as Mr. B.
As Mr. B and as Mr.
Hardworking.
C.
So A equals to B equals to C equals to D equals to 0. Do you remember that in null hypothesis, the variance equals to 0? There is no difference between the first person
Yes.
and the second person. So that is
Yeah.
a null hypothesis. So that is an experiment. An experiment is meant to identify a typical population. It is not for a known fact. So a known
Okay.
fact is when the data has already been distilled. Like you talked about leap year, that's already
Excuse
been
me.
distilled out. You have the data there. So you can only sort the data. You are not conducting an experiment. Understand? You cannot say
Yeah.
2021 is a leap year. No, because it is already there that 2021 is not a leap year. But if you say have something that is typical about that population, so somebody might query it and you now conduct a research. So that would be the null hypothesis. Now, you now decide to take observations of the population. Then you conduct the experiment, taking whatever you have observed, the data, the variables, and using the null hypothesis. Yesterday, we tried to explain what we call experimental units and measurement units. I don't know if you watch that video.
I started watching it.
Okay.
I didn't
Exper-
finish it.
Experimental unit, after picking, before you are able to get the data, you must likely look at several factors. We talked about factors. In every population, there are factors, and factors have levels. The levels of treatments make up a factor. We have age factor, we have educational factor, we have occupational factor, we have gender factor. I hope you understand. So
Yeah, I understand.
within the factors, there are levels of treatment. What I mean by levels of treatment is this. You cannot apply the same measurement unit on a particular level within a factor. So you must look at what level of factor am I considering in my experiment. You are talking of people that are hardworking. Yeah. Can somebody that is less than 18 years be considered to be hardworking? Those are questions. Can the person be qualified to be experimented upon? Can someone who is not above a particular educational qualification be considered to be hardworking? Let's say somebody cannot read, cannot write. How do we qualify the person such that he becomes a member of the data that we want to conduct the experiment? These are things that affect experiments. So an experiment should be designed in such a way that each factor, in particular, or several kind of levels are targeted. So you cannot just generalize. So you must be able to group your population in such a way that you are able to conduct the experiment. Then ability to define how you structure and divide. You might divide Akwa Ibom State into 31 local governments. After dividing it into 31 local governments, you might consider the population density of each local government. And you might consider where the working class are likely to settle. These things must be part of your design. After that, once you are able to get that, that is what we call experimental units. Then sampling. You might say, I want to sample by percentage of the population, 1% or 0.05% of the population or 0.01% of the population in each of the local government. That is a smaller population to the bigger population. Now, you sampling
Hello.
each. Are you hearing me? Are you there, Mr. Isaac? Hello.
Yeah, I lost network.
Okay. I hope you are back. I was okay. Let me see. I am trying to explain what I explained yesterday. Like once a scientific question comes up, we talk about null hypothesis. Then for us to get the variables, the observed random variables, we must first of all understand how we are going to get this data. We have experimental units and we have measurements units. Now, our question was, okay, somebody made a statement. Typical Akwa Ibomite is hardworking. Now, because of that statement, a research was to be conducted. And that research, the null hypothesis is that every Akwa Ibomite is hardworking. So A equals to B equals to C equals to D, like that to infinity, then equals to 0, which means everybody are equally hardworking. That is what we want to test of the population in Akwa Ibom State. I hope we get there. Now, we cannot just sit here in Uyo and test for Akwa Ibom State. We must, in our experiment, if we sit in Uyo and test about Akwa Ibom State, our experiment will be biased. We will discover that there are a lot of people not from Akwa Ibom State who will make up members of that population. And these people might just be coming from other states to do business here and go back. They might be on transit. We might have a problem. Now, if we say, let's speak Igor Ekpene, Oron, Eket, might also be biased, because we might discover that there's somebody that is very hardworking, a typical Akwa Ibomite, but is living in Orogonam. Very hardworking, works very hard, and he contributes far more to the progress of the state economic-wise than every other person. So for us to be able to bring down those bias, we now split Akwa Ibom into experimental units. I was saying, we might say, okay, let's consider the local government, 31 local governments. Or then we now say, what are the population of each local government? And we can decide to sample a fraction, let's say 1/1000 of each population living within that local government. We have designed how our experiments will look like. Now, where our random variables will come, the randomization now, is that we are not specific that when we go to that local government, we go straight to the local government headquarters. No. We might say, once we get to the local government, we throw a dice or we run a computer number. So whatever the number gives us, we count. If it gives us 15, which means we might target the 15th person that we met in that local government to add him to our experiment. We assess him, we get the data. We throw another dice and it tells us the 6th person. We now go to the 6th person that we met. We randomly throw another dice and it tells us that we are going to another 7th person. So we start. After we had met with the 15th person, then we had counted 6th person and met another person. So we now count another 7 person and now meet this other person. This is where randomization comes in. the data volunteers itself has what we call equal chance of being taken or not being taken. You were not biased. You did not say, oh, I know that man is very hardworking. Let me go and assess him. So we talked about randomization in data collection. Ability for each data to have an equal chance of being there in the experiment. So once you are able to gather the data, you get the fraction that you needed from that particular subpopulation. Probably it was 1/1000 of that population. You do the same in other population. After gathering the data, what are they doing? How are they contributing to the economy? Are they able to deliver whatever work they are doing with, the test questions now that you designed? You now go and that forms part of the experiment. Saying you now go get your sample results, the data. Then you do some statistical analysis, and then you test the hypothesis given the p-value. If the p-value tends to 0, then we are likely to say that I think if a p-value tends to 0, we are likely to either accept this hypothesis that the first person is as hardworking as the other person. No, I think probability value. Okay, it's a probability that this null hypothesis will be rejected. So once the probability tends to 0, we know that we cannot reject this one. It doesn't mean that this hypothesis is outly correct. It means that we don't have any evidence to reject that A is as hardworking as B, who is as hardworking as C, such that whatever variance we can have among them equals to 0 or tends to 0. Let's not use the word equal. So once we are done with this is another scientific question might come up from this experiment. Somebody might ask, what now makes these people hardworking? Are you getting what I'm saying? So because all experiments goes back to another question, a scientific question. So somebody will ask, well, what now makes these people hardworking? I hope we understand now. So this experiment, the results of the experiment, everything we deduce from the experiment, all the data and statistical analysis, the observations, each member of that population, a typical member has at least a typical attribute, one observable thing about that data. I hope we get that point. Are we there?
Yes, we are. Okay, yes, I am.
So I've been
Yes,
able
yes,
to
I am.
summarize some of the things I said yesterday. So all this are the same thing, but this is more expanded. So if you look at This EDMA means, I think it's experimental data analysis. That is what the EDA. I want to see the abbreviation that you add here so that you can follow this text properly. Okay, that's page 21. We are still going to go this. I've explained this. Now, this is where I intended to start, but I'll be brief, probably 5 minutes. Defining and classifying data variables. This is where the problem of experiments always comes. So a key component of design of experiments is operationalization, which is the formal procedure that links scientific concepts to data collection. Operationalizations define measures or variables which are quantities of interest or which serve as practical substitutes for the concept of interest. For example, if you have a theory about what affects people's anger level, you need to operationalize the concept of anger. Like we talked about hardworking, we might just have an idea of hardworking, but there are more things under being hardworking. You might measure anger as the loudness of a person's voice in decibels or summary features of a spectral analysis of a recording of their voice, or places where the person places a mark on a visual analog anger scale, or their total score on a brief questionnaire. Each of these is an example of operationalization of the concept of anger. When we were in school, most times we are always taught to believe that our project work must be in a certain way, but it is not supposed to be. Data can be obtained from by any format. Somebody might decide, I want to be a person that observes my data, not necessarily issuing questionnaires. Experiments have their original bias dependent on the design. But most times we try as much as possible to design our experiment with so much randomization. With the randomization, we are able to limit the bias of the design of the experiment. I hope we understand that. You cannot tell a person, this is how I want you to get the data, because the person has an idea in his mind. The experiment is supposed to answer the question in the person's mind. The design itself can be a bias, but what makes the design unbiased is the randomization of the variable. So have you seen that there are different ways somebody can decide to measure anger? Not necessarily via questionnaire. You might say, okay, let me record everybody I come across. If somebody shouts this way, the person is angry. If the person does not shout, the person is not angry. Or if somebody frowns his face, the person is angry. If somebody does not frown, his face. The person is not angry. So what now makes the experiment unbiased is not the biased design, it's the randomness of the data, such that you don't say, okay, I know that man is always frowning. Let me go and see if he's frowning. But ability to say, okay, who should I pick? And you don't do it haphazardly. You must have it a design to get that randomness. You might say, everybody who crosses this particular road, I'm going to check if the person is angry or not by the facial expression. So you did not tell the person to cross the road. You are just there looking at everybody that wants to cross the road at that particular point. So anybody that goes and stand at that point that you marked to cross the road, you use that person automatically becomes a member of your data. The person is independent of the experiment. It's independent of the other person. He doesn't know what made this other person to frown his face. He is just frowning, or that is how he's just keeping his face. He did not tell you he is frowning. You are the one that decides that if he's not keeping his face this way, he is frowning. If he keeps this other way, he is not frowning. I hope we understand this thing. So
Slowly,
designs
yes.
are
Okay.
such that they are subjective. But what makes a design unbiased is the randomness of the data. So I I need to hammer on this because it makes people feel that they are not doing collecting good data. Now, what makes a good variable? Regardless of what we are trying to measure, the qualities that make a good measure of a scientific concept are high reliability, absence of bias, low cost, practicality, like I just explained, objectivity, high acceptance, high concept validity. Reliability is essentially the inverse of the statistical concept of variance, and a rough equivalence is consistency. Statisticians also use the word precision. So we will skip all this definition, but let's take the definition of bias. Bias refers to the difference between the measure and some true value. A difference between an individual measurement and a true value is called an error, which implies the practical impossibility of a perfect precision rather than the making of mistakes. The bias is the average difference over many measurements. Ideally, the bias of a measurement process should be zero. For example, a measure of weight that is made with people wearing their street clothes and shoes has a positive bias equal to the average weight of the shoes and clothes across all subjects. So that is the man's explanation here. So okay, this one talks about concept validity. Now, classification by rule. There are two different independent systems of classification of variables that you must learn in order to understand the rest of this book. The first system is based on the role of the variable in the experiment and the analysis. The general terms used most frequently in this text are explanatory variables versus outcome variables. So explanatory variables are the x's. Then the outcome variables are the y's. I hope you understand. When we say y is what we always look for. Sorry, y is
Yeah.
always what we use as the outcome, what we observe. Then x is what we go out there. Sorry, y is actually what we are seeing and we want to solve it as a problem. Like when we ask that question, we say anybody that frown. So each variable goes to frown or not frowning. So those are the outcome. Then the ones that explain to us whether they are frowning or not is the x variable, which is what we are observing there. We might say if the person is not showing his teeth, the person is frowning. Or if the person is not showing his teeth, but keeps a lighter face and is a facial expression, the person is not frowning. So that is still an explanatory variable. We might have up to 3 or 4 explanatory variables. We might say not showing his teeth and his jaw is popping out. This one not showing his teeth, but is keeping a relaxed face. This one not showing his teeth or showing his teeth, but it's grinning. This one showing his teeth, but smiling. Those are 4 different variables. So we might be collecting the variables and group them by certain points. The lower the point, which shows that the person is actually angry. The higher the point shows that the person is not angry. We might say if the person is opening his teeth and also smiling, the person can score 5. Then the other person, like that, up to the lowest, which is 1. So 1 shows the person is actually angry. So we now use facial expression to tell ourselves somebody is angry or not. So those are explanatory variables. Then the outcome is once we get it, whatever result it gives us becomes the outcome, which is the y. So I think we'll likely stop there because this is more like continue from what we did yesterday. I did make similar explanation either way, but this one is more elaborate because it talks about how it varies, the variance and covariance. Please ask questions so that I don't take much time. I want us to take this thing step by step.
Yes, sir. Thank you very much for the lecture.
All right.
Yeah, though I joined late, but I think I was able to pick up things. But okay, my question is not related directly to the lecture. I just want to ask about the data analysis class that was talked about on WhatsApp.
Yes, I
What did that hold?
we had a volunteer who wanted to take that class. So
Okay,
on he tells us that he's going
okay,
to
okay. Like the time will be communicated on WhatsApp, right?
yes.
Oh, yeah, thank you, sir.
You're welcome. Any other
Yeah,
question?
I really have no question per se on this. Maybe when I go through the material again and I have any question, I will ask.
I did a little of not a little. I did agricultural statistics.
Okay.
All I think So I'll have to go look through them again. But what was taught today, I understood. I think 80%, just to refresh my memories.
The idea of this class is not for us to go looking for data, but to understand for each experiment what kind of analysis we need. So that is where we are driving at.
Okay, yeah, to understand the
Yes, we
concept.
want to know from a statement, somebody, like I said, somebody might make a statement and some other person counters it. From the counter statement, an experiment can be conducted. I hope you understand it.
Yeah.
So it doesn't mean that everything has to be perfect. All right. So
Okay.
we are going to round up this class. And uh, go back Rotimi. I hope I pronounced correctly. Say bye-bye and we end the class.
Okay, thank you very much, sir.
He said you should pray and we end the class.
All right, we
It's
give
not.
I think we, we give thanks to God for this day. We ask for his guidance. We thank him for giving us the opportunity and privilege to have class. We bless his holy name. We ask that he continues to guide us through until we are successful. In Jesus' name, amen.
Amen.
All right, good night.
Good night.